Have you ever looked up at the sun and wondered what would happen if it just vanished? Not gradually dimmed over billions of years like scientists tell us it will, but actually exploded tomorrow morning at exactly 9:47 a.m. while you're sipping your coffee and scrolling through your phone. The answer isn't just terrifying, it's so profoundly catastrophic that it challenges everything we think we know about survival, physics, and what it truly means to exist in this fragile bubble we call Earth. Wherever you are in the world right now, I hope you're somewhere comfortable because we're about to embark on a journey that will fundamentally change how you see that bright star hanging in our sky. Tonight, we're going to explore one of the most haunting what-if scenarios in all of science. What would actually happen if our sun exploded tomorrow? Now, before we dive deep into this cosmic nightmare, I want you to know something. This isn't just another doomsday video designed to keep you awake at night. This is a carefully crafted exploration of physics, biology, and the delicate dance of forces that keep us alive every single second of every single day. And by the end of this journey, you'll understand not just how we would die, but why the fact that we're alive right now is so extraordinarily miraculous that it defies comprehension. The visuals are here to guide you through this story, but feel free to close your eyes and let your imagination paint the pictures. Sometimes the mind's eye sees more clearly than any screen ever could. And if you find yourself drifting off somewhere in the middle of this cosmic catastrophe, well, that's perfectly fine. At least you'll have pleasant dreams instead of contemplating the end of everything you've ever known. I'd love to know where you're watching from tonight. Drop your location in the comments below. Let's start. Now, let's address the elephant in the room. The sun can't actually explode tomorrow. Our star is what astronomers call a main sequence star, and it's got roughly 5 billion years of steady burning ahead of it before it even begins to think about dying. When it does eventually die, it won't explode like a supernova. It'll expand into a red giant, swallow Mercury and Venus, and then gently shed its outer layers to become a white dwarf. It's a slow, predictable death that gives any future civilizations plenty of time to pack up and move somewhere else. But here's the thing about thought experiments. They don't have to follow the normal rules of stellar evolution. They're designed to push the boundaries of our understanding and explore scenarios that reveal fundamental truths about how our universe operates. So for the next hour, we're going to pretend that physics has taken a holiday and our perfectly stable, middle-aged star has decided to go out with the biggest bang in the solar system. Picture this moment. It's tomorrow morning, and you're going about your normal routine. Maybe you're making breakfast, getting ready for work, or checking your phone for the latest news. The sun is shining through your window exactly as it has every morning for your entire life. Everything seems perfectly normal, perfectly safe, perfectly predictable. And then, at exactly 9:47 a.m., something impossible happens. Deep in the sun's core, the delicate balance between gravity crushing inward and nuclear fusion pushing outward suddenly breaks down. Instead of the gradual changes that should take billions of years, everything goes wrong all at once. The sun doesn't just burn brighter or flicker, it explodes with the force of billions of hydrogen bombs detonating simultaneously. But here's what makes this scenario so fascinating from a physics perspective. You wouldn't know it happened for 8 minutes and 20 seconds. That's how long it takes light to travel the 93 million miles from the sun to Earth. So while our star is busy destroying itself in the most spectacular explosion the solar system has ever seen, you're still making your coffee, completely oblivious to the fact that your world has already ended. This 8-minute delay reveals something profound about the nature of reality itself. Information, including the information that the sun has exploded, can only travel at the speed of light. Nothing in the universe can exceed this cosmic speed limit. So even though the sun exploded at 9:47 a.m., the news of that explosion is still racing through space at 186,282 miles per second, carrying with it the end of everything we've ever known. During those 8 minutes and 20 seconds, Earth exists in a strange liminal space. The sun has already died, but from our perspective, it's still shining. We're living in the last moments of a world that no longer has a star, but we don't know it yet. It's like being in a house that's already on fire, but the smoke hasn't reached your room. You feel safe. But safety is just an illusion created by the finite speed of light. Think about what's happening during this cosmic grace period. Children are playing in parks, warmed by sunlight that started its journey when the sun was still alive. Plants are still photosynthesizing, converting light energy into chemical energy, unaware that their energy source no longer exists. Birds are singing, bees are buzzing, and life on Earth continues exactly as it has for billions of years, completely ignorant of the wave of destruction racing toward them at light speed. This scenario reveals the strange relationship between cause and effect in our universe. The cause, the sun's explosion, has already happened, but the effect, the arrival of that explosion's energy at Earth, is still 8 minutes away. We're living in a bubble of false normalcy, protected only by the cosmic speed limit that governs how quickly information can travel through space. But eventually, those 8 minutes run out. At exactly 9:55 and 20 seconds a.m., the first light from the exploded sun reaches Earth. And this isn't the gentle, life-giving sunlight we're used to. This is the concentrated fury of a star that has turned itself inside out, releasing more energy in a single moment than it normally produces in millions of years. The first thing you would notice, if you happen to be looking in the sun's direction, is that it suddenly becomes impossibly bright. Not just bright, like looking directly at the sun on a clear day, which is already dangerous enough to cause permanent eye damage. This is bright in a way that has no comparison in human experience. Imagine every spotlight at every stadium in the world focused directly on your face, then multiply that by a number so large it defies comprehension. This initial burst of light isn't just visible light, it's a full spectrum assault of electromagnetic radiation. Gamma rays, X-rays, ultraviolet light, visible light, infrared, microwaves, and radio waves all racing toward Earth in a concentrated beam of stellar death. The gamma rays and X-rays, the most energetic forms of electromagnetic radiation, arrive first because they all travel at the speed of light, but they carry enough energy to kill you instantly. If you are unlucky enough to be on the day side of the planet seconds of when they arrive, within that first flash, the Earth's atmosphere begins to change in ways that would make climate change look like a gentle breeze. The intense radiation starts breaking apart the molecules in our upper atmosphere, particularly the ozone layer that normally protects us from harmful ultraviolet radiation. Nitrogen and oxygen molecules, which have been happily floating around in the stratosphere for millions of years, suddenly find themselves torn apart by gamma rays carrying more energy than they've ever encountered. This isn't a gradual process. We're not talking about the slow deterioration of the ozone layer that scientists worry about due to human activity. This is the complete annihilation of our atmospheric protection in a matter of minutes. The ozone layer, which took millions of years to form and has been faithfully protecting life on Earth from harmful radiation, simply ceases to exist. But the light show is just the opening act. Remember, when a star explodes, it doesn't just release energy in the form of electromagnetic radiation. It also hurls massive amounts of matter into space at incredible velocities. The sun's outer layers, which normally take thousands of years to shed small amounts of material as solar wind, are suddenly blasted outward at speeds of thousands of miles per second. This creates what astronomers call a shock wave, a wall of superheated stellar material racing through the solar system like a cosmic tsunami. Unlike the electromagnetic radiation, which travels at light speed, this shock wave moves much more slowly. But slowly is a relative term when we're talking about stellar explosions. This wall of death is moving at roughly 3% of light speed, which means it will take about 4.5 hours to reach Earth after the initial light burst. So here's where our timeline gets truly terrifying. At 9:55 a.m., the electromagnetic radiation arrives and begins destroying our atmosphere. By 10:30 a.m., anyone on the day side of the planet who was looking toward the sun is either blind or dead from radiation exposure. By noon, the ozone layer has been completely destroyed and harmful ultraviolet radiation is pouring through the atmosphere unfiltered. But the real apocalypse is still 4 hours away. At 2:25 p.m., the shockwave arrives. This isn't just a wall of hot gas. This is a tsunami of stellar material moving at 9 million miles per hour, carrying with it temperatures of millions of degrees and enough kinetic energy to sterilize entire planets. When this shockwave hits Earth's magnetic field, something extraordinary happens. Our planet's magnetic field, which normally does a good job of deflecting the gentle solar wind and protecting us from cosmic radiation, is completely overwhelmed. It's like trying to stop a freight train with a spider web. The magnetic field doesn't just fail, it gets blown away entirely, leaving Earth completely exposed to the full fury of the stellar explosion. The shockwave doesn't stop at our magnetic field. It slams into Earth's atmosphere with enough force to strip away most of it entirely. The same atmosphere that has been protecting and nurturing life for billions of years gets peeled away like the skin of an orange, blown off into space by the sheer violence of the stellar explosion. This atmospheric stripping isn't a gentle process. As the shockwave tears through our air, it compresses and heats the atmosphere to temperatures of thousands of degrees. The sky literally catches fire. Every molecule of nitrogen and oxygen in the atmosphere becomes part of a planet-wide inferno that makes forest fires look like birthday candles. But even this atmospheric incineration pales in comparison to what happens to Earth's surface. The shockwave doesn't just heat the atmosphere, it heats everything it touches. The oceans, which cover 71% of our planet's surface and contain enough water to fill 1.37 billion cubic kilometers of space, begin to boil. Not just at the surface, like a pot of water on a stove. The entire ocean, from surface to sea floor, starts turning into steam. All 1.37 billion cubic kilometers of water. Every drop that has ever fallen as rain, every wave that has ever crashed on a beach, every tear that has ever been shed, begins its transformation from liquid to gas. This oceanic boiling creates a feedback loop that accelerates Earth's destruction. As the water turns to steam, it rises into what's left of the atmosphere, creating a thick blanket of water vapor that traps even more heat from the stellar explosion. It's like wrapping the planet in a cosmic oven, ensuring that every surface reaches temperatures hot enough to melt rock. The continents fare no better than the oceans. The same shockwave that's boiling the seas is simultaneously heating the land to temperatures that exceed those found in steel foundries. Mountains that have stood for millions of years begin to glow red hot. Forests don't just burn, they vaporize instantly, leaving nothing but superheated gas where mighty trees once stood. Cities, Those monuments to human civilization that we've spent thousands of years building melt like ice cubes in a furnace. The steel and concrete that form our skyscrapers, the asphalt that paves our roads, the plastic and metal that make up our cars, all of it transforms from solid matter into glowing liquid and then into gas. But perhaps the most haunting aspect of this scenario is how quickly it all happens. From the moment the shockwave arrives until the complete sterilization of Earth's surface takes less than an hour. Billions of years of evolution, millions of years of geological processes, thousands of years of human civilization, all erased in less time than it takes to watch a television program. Yet even as we contemplate this cosmic catastrophe, there's something strangely beautiful about it. This isn't just destruction, it's transformation on a scale that's almost impossible to comprehend. Every atom that makes up your body, every molecule of water in the ocean, every grain of sand on every beach gets recycled back into the cosmic elements from which they came. The carbon in your muscles, forged billions of years ago in the nuclear furnaces of ancient stars, returns to space as superheated gas. The calcium in your bones, created when massive stars collapsed and exploded long before our solar system even existed, gets launched back into the cosmos to eventually become part of new worlds, new possibilities, new forms of life we can't even imagine. This is the strange poetry of stellar death. What seems like ultimate destruction is actually the universe's way of recycling itself, of taking the building blocks of one world and scattering them across space to become the foundation of countless others. Your atoms, the very matter that makes you who you are, will survive this apocalypse and travel through the galaxy for millions of years before settling down to become part of something entirely new. But let's zoom out from this cosmic recycling program and consider what's happening to the other planets in our solar system. Because Earth isn't the only world feeling the fury of our exploded star. The same shockwave that's currently sterilizing our planet is racing outward in all directions, carrying stellar death to every corner of the solar system. Mercury, that small, rocky world closest to the Sun, doesn't stand a chance. The shockwave hits it just minutes after leaving the Sun's surface, and Mercury simply ceases to exist as a planet. The temperatures are so extreme, the energy's so vast, that the entire world gets vaporized instantly. One moment it's a planet with mountains and craters, and a fascinating history of impacts and volcanic activity. The next moment it's nothing but a cloud of superheated gas expanding into space. Venus, our hellish neighbor, with its crushing atmosphere and surface temperatures hot enough to melt lead, fares no better. Despite having the thickest atmosphere of any rocky planet in our solar system, despite being shrouded in clouds of sulfuric acid that have protected it from millions of years of asteroid impacts, Venus gets obliterated just as thoroughly as Mercury. Its dense atmosphere, which normally creates a greenhouse effect so intense it makes Venus hotter than Mercury despite being farther from the Sun, provides no protection against the stellar explosion. The shockwave tears through those sulfuric acid clouds like they're made of tissue paper and reduces the entire planet to its component atoms. Mars, the red planet that has captured human imagination for centuries, meets a similar fate but with a delay that makes its destruction somehow more poignant. The shockwave takes longer to reach Mars because it's farther away, giving the planet about 15 extra minutes of existence after Earth has already been sterilized. For those 15 minutes, Mars continues its ancient rotation, its polar ice caps still glinting in the light of a star that no longer exists, its rusty surface still bearing the scars of ancient rivers and the tracks of human rovers that explored its mysteries. But eventually, the wall of stellar death reaches Mars too. The thin atmosphere that has been slowly leaking into space for billions of years gets stripped away entirely in seconds. The polar ice caps, which contain enough frozen water to cover the entire planet in a layer several feet deep, sublimate directly from ice to steam and then get blown away into space. The red iron oxide that gives Mars its distinctive color, the result of billions of years of oxidation processes, gets heated to temperatures that break apart the molecular bonds and scatter the individual atoms across the solar system. Even the asteroid belt, that collection of rocky debris orbiting between Mars and Jupiter, doesn't escape the stellar explosion. Thousands of asteroids, some as large as mountains, others no bigger than boulders, all get swept up in the expanding shockwave. These chunks of rock and metal, which have been peacefully orbiting the Sun for billions of years, suddenly find themselves part of a cosmic sandstorm moving at thousands of miles per second. Ceres, the largest object in the asteroid belt and the only dwarf planet in the inner solar system, shares the fate of its smaller neighbors. This ancient world, which contains about a third of all the mass in the asteroid belt and harbors a subsurface ocean that might have supported primitive life, gets heated to the point where its rocky surface melts and its hidden ocean boils away into space. But here's where our story takes an interesting turn. As we move farther out from the Sun, the effects of the explosion become more complex and, in some ways, more fascinating. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, are so far away and so massive that they don't get completely destroyed like the rocky inner planets. Instead, they undergo transformations that reveal the true power and complexity of stellar explosions. Jupiter, that magnificent giant with its swirling of moons, sits storms and dozens about 5 times farther from the Sun than Earth. This distance means the shockwave takes several hours longer to reach it, and by the time it arrives, it has spread out and cooled somewhat. Jupiter doesn't get vaporized like the inner planets, but it doesn't escape unscathed either. The shockwave slams into Jupiter's upper atmosphere with enough energy to heat the entire planet to temperatures of thousands of degrees. The Great Red Spot, that massive storm that has been raging for centuries and could swallow Earth whole, gets disrupted and eventually dissipates as the planet's entire atmospheric circulation system gets thrown into chaos. The bands of clouds that give Jupiter its distinctive striped appearance, created by complex interactions between the planet's rapid rotation and its atmospheric chemistry, get mixed and heated until they lose their organized structure entirely. But Jupiter's transformation goes deeper than just atmospheric disruption. The intense heating from the shockwave causes the planet's atmosphere to expand dramatically. Jupiter, which is already the largest planet in our solar system, swells to many times its normal size as its hydrogen and helium atmosphere gets superheated and expands into space. This expansion has catastrophic consequences for Jupiter's moons. Io, Europa, Ganymede, and Callisto, those 4 Galilean moons that have fascinated astronomers for centuries, find themselves suddenly orbiting inside Jupiter's expanded, superheated atmosphere. It's like trying to orbit inside a star. The tidal forces, already strong due to Jupiter's massive gravity, become even more extreme as the moons plow through the expanded atmosphere. Europa, that ice-covered moon with its hidden subsurface ocean that might harbor life, suffers a particularly tragic fate. The shockwave's energy melts its ice shell entirely, exposing the ocean beneath to the vacuum of space. Any life that might have evolved in that dark, hidden sea gets flash frozen and then sublimated away as the ocean boils into the vacuum. Io, with its active volcanoes powered by tidal heating from Jupiter's gravity, experiences volcanic eruptions on a scale never seen before. the entire moon becomes one massive volcano, spewing molten rock and sulfur compounds into space at velocities high enough to escape the moon's gravity entirely. Within hours, Io transforms from a solid world into a dispersing cloud of volcanic debris. Saturn, with its magnificent ring system and collection of diverse moons, undergoes a transformation that's both beautiful and terrifying. The shockwave's energy heats Saturn's atmosphere just as it did Jupiter's, causing the planet to expand and glow with thermal radiation. But the most spectacular change happens to Saturn's rings. Those iconic rings, made of countless chunks of water ice ranging in size from tiny particles to house-sized boulders, begin to sublimate and disperse as the shockwave's energy heats them beyond their vaporization point. The ring system that has existed for millions of years, creating one of the most beautiful sights in the solar system, disappears in a matter of hours as billions of ice particles turn to steam and blow away into space. Titan, Saturn's largest moon and the only moon in the solar system with a substantial atmosphere, experiences changes that would be fascinating if they weren't so destructive. Titan's thick atmosphere, composed primarily of nitrogen with traces of methane and other hydrocarbons, gets superheated by the shockwave's energy. The methane lakes and rivers that dot Titan's surface, some of the most exotic geological features in the solar system, boil away into the expanding atmosphere. The complex organic chemistry that has been taking place in Titan's atmosphere for millions of years, creating the orange haze that shrouds the moon's surface, gets disrupted as temperatures rise to levels that break apart the organic molecules. This moon, which some scientists think might represent an early Earth-like environment, loses its unique characteristics and becomes just another superheated world orbiting a glowing gas giant. As we venture even farther from the Sun, to the ice giants Uranus and Neptune, we encounter worlds so distant that the shockwave takes many more hours to reach them. By the time the stellar explosion's energy arrives at these remote planets, it has spread out over such a vast area that its effects are somewhat diminished. But somewhat diminished doesn't mean negligible when we're talking about the explosive death of a star. Uranus, that strange world tilted on its side with its peculiar magnetic field and faint ring system, experiences atmospheric heating that disrupts its unique weather patterns. The planet's blue-green color, caused by methane in its atmosphere absorbing red light, changes apart meth as the shockwave's energy break insane molecules and alters the atmospheric chemistry. Neptune, the windiest planet in the solar system, with storms reaching speeds of over 1,000 miles per hour, finds its atmospheric dynamics completely transformed. The Great Dark Spot, Neptune's equivalent of Jupiter's Great Red Spot, gets disrupted and eventually disappears as the planet's entire atmosphere gets heated and its circulation patterns get thrown into chaos. But perhaps the most poignant casualties of our stellar explosion are the small, icy worlds of the outer solar system. Pluto, no longer classified as a planet, but still a fascinating world with its heart-shaped nitrogen plains and complex relationship with its moon Charon, experiences changes that reveal the far-reaching effects of stellar death. The shockwave's energy, though greatly diminished by the time it reaches Pluto's distant orbit, still carries enough heat to begin sublimating the nitrogen and methane ices that coat Pluto's surface. The thin atmosphere that Pluto occasionally develops when its elliptical orbit brings it closer to the Sun becomes much thicker as surface ices vaporize. For a brief time, this distant world experiences something like weather as its surface transforms from solid to gas. Charon, Pluto's largest moon, undergoes similar changes. The water ice that makes up much of Charon's surface begins to sublimate, creating a temporary atmosphere around this usually airless world. The two objects, locked in their eternal dance around their common center of mass, continue their cosmic waltz, even as they're being slowly transformed by the energy from our exploded star. Beyond Pluto, in the Kuiper Belt and the even more distant Oort cloud, billions of comets and asteroids feel the touch of stellar death. These ancient remnants from the formation of our solar system, some of which have remained unchanged for over 4 billion years, begin to experience their first significant heating since the early days of the solar system. Comets that normally develop their characteristic tails only when they venture close to the sun suddenly find themselves warming up in their distant orbits. The water ice, frozen carbon dioxide, and other volatile compounds that make up these dirty snowballs begin to sublimate, creating temporary atmospheres and tails even in the outer reaches of the solar system. This cosmic heating of the outer solar system creates one of the most beautiful and tragic spectacles imaginable. Millions of comets, spread across a volume of space larger than many star systems, begin to glow and develop tails simultaneously. If there were any observers left alive to witness it, they would see the entire outer solar system light up like a vast cosmic Christmas tree, with millions of points of light suddenly becoming visible as ancient comets wake up from their billion-year slumber. But this beauty comes at the cost of destruction. Many of these comets, heated for the first time in their existence, lose so much mass to sublimation that they break apart entirely. Others get their orbits altered by the pressure of the expanding shockwave, sending them on new trajectories that might eventually take them out of the solar system entirely. The gravitational dynamics of the outer solar system, stable for billions of years, get disrupted as the shockwave's pressure and the heating of countless small bodies create tiny but cumulative changes in orbital mechanics. Some objects get nudged into slightly different orbits. Others get accelerated to escape velocity and begin their journey into interstellar space, as the former contents of our solar system scatter across the galaxy. As we watch our solar system transform into this cosmic light show of dying worlds and glowing debris, we need to pause and consider something that might seem almost trivial in the face of such overwhelming destruction. What happens to the spacecraft we've sent into the void? Those mechanical ambassadors of human curiosity that are, even now, wandering through interstellar space, carrying messages from a civilization that no longer exists. Voyager 1 and Voyager 2, those remarkable machines launched in 1977 to explore the outer planets, are currently billions of miles away from the Sun, having crossed into interstellar space years ago. When our star explodes, these spacecraft become something unprecedented in human history. They become the only surviving artifacts of our entire civilization, the last physical evidence that Earth ever existed, that humans ever walked on a small blue planet orbiting an ordinary star. The shockwave from our exploded sun will eventually reach these distant travelers, but by then it will have weakened considerably. Instead of vaporizing them instantly, like everything else in our solar system, the Voyagers will experience something more subtle, but equally profound. The gentle push from the expanding stellar debris will accelerate them slightly, sending them deeper into interstellar space at velocities they were never designed to achieve. Each Voyager carries a golden record, a collection of sounds and images from Earth, intended to tell the story of our world to any alien intelligence that might find them. Music from Bach and Beethoven, greetings in dozens of human languages, the sound of ocean waves, and photographs babies crying of forests and cities and human faces. These records, designed originally as a hopeful message to the cosmos, become something far more poignant. They become tombstones, the only remaining evidence of a world that dared to reach beyond itself, even as it lived under the light of a star destined to destroy it. But here's where our story takes a turn towards something even more profound than planetary destruction. Because while we've been focusing on the death and transformation happening within our solar system, we haven't yet considered what this explosion means for the broader cosmos. Our sun's death doesn't occur in isolation. It sends ripples through space and time that will be felt by other star systems, other worlds, other possible civilizations scattered across our corner of the galaxy. The energy and matter ejected from our exploded star will travel stellar space for through into thousands of years, carrying with it the atomic building blocks of everything that once existed in our solar system. The calcium from your bones, the iron from your blood, the carbon from your DNA, all of it gets dispersed across hundreds of cubic light years of space, creating an expanding bubble of enriched interstellar medium. This stellar debris doesn't aimlessly through the void. It carries just drift with it the potential for new creation. When this material eventually encounters vast clouds of interstellar gas and dust, it will trigger the formation of new stars, new planets, new possibilities for life. The atoms that once made up Earth's oceans will help form the atmospheres of distant worlds. The elements that once comprised human civilization will become part of alien landscapes we can't even imagine. In this sense, our sun's explosion becomes an act of cosmic generosity. What appears to be ultimate destruction is actually the universe's way of spreading the building blocks of complexity and life across vast distances. Every atom that gets blasted away from our dying solar system carries within it the potential to become part of something magnificent and new. But this cosmic recycling process takes place on timescales that dwarf human comprehension. The shockwave from our exploded sun will take roughly 60,000 years to reach the nearest star system. During that time, the expanding bubble of stellar debris will encounter other stars, other planets, other forms of matter and energy that will alter its composition and trajectory in ways we can barely predict. Some of this material will get captured by the gravitational fields of other stars, falling into their nuclear furnaces to be fused into even heavier elements. Other portions will remain in interstellar space for millions of years, slowly cooling and condensing until they become part of the cosmic dust that fills the galaxy. Still other fragments will achieve such high velocities that they escape our galaxy entirely, carrying the remnants of our solar system into the vast emptiness between galaxies. This raises a fascinating question about the nature of existence itself. If the atoms that make up your body right now came from the explosions of ancient stars that died billions of years ago, and if those same atoms will someday become part of new stars and planets and possibly new forms of life, then in what sense do you actually die when our sun explodes? Your physical form gets destroyed, certainly. Your consciousness, your memories, your personality, all of that gets obliterated in the stellar inferno. But the fundamental building blocks of your existence, the actual matter that makes you who you are, continues its journey through the cosmos. This perspective transforms our hypothetical solar apocalypse from a story of ending into a story of transformation. We're not just witnessing the death of worlds, we're witnessing the birth of new possibilities scattered across space and time. The explosion that destroys our solar system simultaneously plants the seeds for countless future solar systems, some of which might harbor forms of life more complex and beautiful than anything that ever existed on Earth. But let's bring our focus back to a more immediate and perhaps more emotionally resonant question. What would it actually feel like to experience this cosmic catastrophe? Not from the perspective of planets or spacecraft or atoms, but from the perspective of a single human being watching their world end in the most spectacular way possible. Imagine you're standing outside when the first light from the exploded sun reaches Earth. Remember, you've had no warning. One moment, the sun looks exactly as it always has. a familiar yellow disk hanging in the blue sky. The next moment, it becomes something beyond description. The sudden increase in brightness is so extreme that it's like looking directly into a welding torch multiplied by 1,000,000,000. The first sensation would be heat. Not the gentle warmth of sunlight on your skin, but the searing heat of a furnace. Within seconds, the temperature around you would rise to levels that make the hottest summer day feel like a cool breeze. Your clothing would begin to smolder, then burst into flames. The grass beneath your feet would brown and wither as if touched by invisible fire, but the heat would be the least of your concerns. The intense radiation flooding Earth would begin breaking down the very molecules that make up your body. The DNA in your cells, those elegant double helices that carry the instructions for life, would start unraveling as gamma rays and X-rays tear through your tissue with enough energy to shatter molecular bonds. If you somehow managed to survive those first few minutes of radiation exposure, you would witness changes in the world around you that would seem like something from a fever dream. The sky would begin to change color as the composition of the atmosphere shifted. The familiar blue would give way to strange hues of red and orange as nitrogen and oxygen molecules got broken apart and reformed into new compounds. The sounds would be unlike anything in human experience. As the atmosphere heated and expanded, you would hear a low, rumbling roar that seemed to come from everywhere at once. This wouldn't be the sound of wind or thunder or any earthly phenomenon. This would be the sound of an entire planet's atmosphere screaming as it got torn apart by forces beyond comprehension. Plants and trees around you would begin to smoke and then ignite spontaneously as their cellular structure broke down under the assault of radiation and heat. Lakes and rivers would start to bubble and steam as their surfaces began the transition from liquid to gas. The very rocks beneath your feet would begin to glow with thermal radiation as they absorbed more energy than they had ever experienced. But perhaps the most haunting aspect of this experience would be the silence that comes after. Once the initial chaos subsides, once the atmosphere has been stripped away and the surface has been sterilized, an absolute silence would descend upon the Earth. No wind, because there's no air left to move. No sound of any kind, because sound needs a medium to travel through, and that medium no longer exists. You wouldn't survive to experience this silence, of course. No complex life could endure the transition from living world to sterile rock. But if you could somehow observe from a safe distance, you would see Earth transform from a vibrant blue and green marble into a glowing red ember, then slowly fade to the cold, dark grey of a dead world. This transformation would be remarkably quick by cosmic standards, but agonizingly slow by human ones. The complete sterilization of Earth's surface would take only a few hours, but those hours would feel like an eternity as you watched everything you had ever known systematically destroyed by the fury of your own star. The psychological impact of witnessing such destruction would be beyond anything humans have ever experienced. We've survived ice ages and volcanic eruptions, wars and plagues, asteroid impacts and climate changes, but we've never faced the complete and total annihilation of our entire biosphere. There would be no hope of survival, no possibility of rebuilding, no chance that some pocket of life might endure to carry on the story of Earth. This absolute finality would create a form of existential terror that our minds aren't equipped to handle. We're used to thinking of disasters as temporary setbacks, challenges to be overcome through ingenuity and perseverance. But there's no overcoming the explosion of your own star. There's no technology that could protect you, no shelter deep enough to hide in, no escape velocity fast enough to outrun the expanding shockwave. In those final hours, as you watched your world die around you, you might find yourself thinking about the strangest things. Not the grand sweep of human history or the meaning of existence, but small, personal details. The smell of coffee in the morning, the sound of rain on your window, the feeling of sand between your toes at the beach. All of these simple pleasures, these tiny moments that make up the texture of human experience, would take on an almost sacred quality as you realized they were about to disappear forever. You might think about the people you love, scattered across the globe, all experiencing their own version of this same cosmic apocalypse. In those final moments, the petty differences that divide humanity would seem absurdly trivial. National borders, political disagreements, cultural conflicts, all of it would be revealed as the meaningless noise it always was in the face of our shared mortality. There would be a strange democracy in this destruction. Rich and poor, young and old, powerful and powerless, all would face the same fate. The explosion of our star would be the ultimate equalizer, treating kings and peasants with identical indifference. No amount of wealth or influence or intelligence could buy you a single extra second of life when faced with the concentrated fury of stellar death. But even in this darkest of scenarios, there might be moments of unexpected beauty. As the atmosphere began to change composition, you might see auroras unlike any that had ever graced Earth's skies. The interaction between the stellar radiation and our planet's magnetic field could create light shows of unimaginable complexity and color, painting the heavens with hues that no human eyes had ever witnessed. The night sky, if you survived to see one final sunset, would be transformed beyond recognition. The familiar constellations, those patterns of stars that have guided human navigation and imagination for millennia, would be joined by new points of light as distant objects got illuminated by the expanding shell of stellar debris. For a brief time, our corner of the galaxy would become visible in ways it never had been before, revealed in the light of our own star's death. These moments of beauty amid the destruction would serve as a reminder of something profound about the nature of the universe. Even in death, even in the most violent and catastrophic events imaginable, there is still room for wonder. The same forces that destroy can also create spectacles of breathtaking magnificence. As we contemplate this scenario, we're forced to confront uncomfortable truths about the fragility of existence and the arbitrary nature of our survival. Every day that you wake up, every breath that you take, every moment of consciousness that you experience depends on the continued stability of a massive nuclear reactor 93 million miles away. The sun's steady burning, which seems so reliable and eternal from our perspective, is actually a delicate balance of forces that could theoretically be disrupted in countless ways. This realization doesn't have to fill you with dread. Instead, it can inspire a profound appreciation for the miraculous nature of ordinary existence. The fact that you're alive right now, reading these words, thinking these thoughts, is so statistically improbable, so dependent on countless factors aligning perfectly, that it borders on the impossible. Your existence requires not just the stability of our sun, but the precise distance of Earth's orbit, the exact composition of our atmosphere, the specific strength of our magnetic field, the particular size of our moon, and thousands of other factors that had to align with mathematical precision. Change any one of these variables by even a small amount, and life as we know it becomes impossible. When we truly understand this cosmic fragility, when we grasp how many things had to go exactly right for us to exist at all, our hypothetical solar explosion becomes more than just a thought experiment about destruction. It becomes a meditation on the preciousness of every ordinary moment. Think about what you did this morning. Maybe you made breakfast, checked your phone, complained about the weather, These mundane activities that seem so trivial, so forgettable, are actually miracles of cosmic engineering. The fact that you can taste food requires billions of years of stellar evolution to create the heavy elements in your taste buds. The fact that you can see your phone screen depends on electromagnetic radiation behaving in precisely predictable ways across 93 million miles of space. The fact that you can think about the weather requires a brain made of atoms forged in the nuclear furnaces of dying stars. Every breath you take contains oxygen created by massive stars that lived and died long before our solar system even existed. Every beat of your heart pumps blood containing iron that was scattered across the cosmos by supernovas billions of years ago. You are, quite literally, made of stardust. And in our hypothetical scenario, you would return to stardust in the most dramatic way possible. But here's what makes this cosmic recycling program truly extraordinary. The atoms that would be scattered when our sun explodes wouldn't just drift aimlessly through space. They would carry within them a kind of cosmic memory, an atomic record of everything they had been part of during their time in our solar system. The carbon atoms that once formed the proteins in your muscles would remember, in their electronic structure, the complex chemistry of life. The hydrogen atoms that once flowed through Earth's rivers would carry traces of the unique isotopic signatures created by billions of years of planetary evolution. The oxygen atoms that once filled your lungs would bear the subtle marks of photosynthesis, that miraculous process that transformed our world from a lifeless rock into a vibrant biosphere. When these atoms eventually encounter new stellar nurseries, vast clouds of gas and dust where future stars are born, they would bring with them the accumulated wisdom of a world that once supported consciousness. In a very real sense, every new star system that forms from the debris of our explosion would contain within it the genetic memory of Earth. This creates a strange kind of immortality. While your individual consciousness would be extinguished in the stellar inferno, the fundamental building blocks of your existence would continue their journey through space and time. Millions of years from now, the calcium from your bones might help form the rocky core of a distant planet. The iron from your blood might become part of an alien mountain range. The carbon from your DNA might find itself incorporated into extraterrestrial life forms that evolve under the light of foreign suns. In this cosmic sense, our sun's explosion wouldn't represent an ending at all. It would represent the most generous act of creation imaginable. By destroying itself, our star would scatter the seeds of future worlds across hundreds of cubic light years of space. Every atom blasted away from our dying solar system would become a gift to the universe, a contribution to the ongoing evolution of matter and energy and complexity. But let's zoom back in from these cosmic timescales and consider what our explosion would mean for the immediate neighborhood of space around our solar system. The shockwave racing outward at 3% of light speed would create effects that extend far beyond the destruction of planets and moons. As this expanding bubble of stellar debris encounters the interstellar medium, the thin soup of hydrogen and helium that fills the space between stars, it would compress and heat this material in ways that trigger the formation of new stars. The shock wave would act like a cosmic matchstick, igniting stellar nurseries throughout our local region of the galaxy. Within a few thousand years of our sun's explosion, dozens of new stars would begin to shine in nearby molecular clouds. These stars, born from the compression waves created by our stellar death, would be fundamentally different from our sun. They would be enriched with the heavy elements scattered from our explosion, giving them the potential to form rocky planets much more quickly than our solar system did. Some of these new stellar systems might develop Earth-like worlds within just a few 100 million years, instead of the billions of years it took for complex life to emerge in our solar system. The heavy elements from our explosion would provide the raw materials for rapid planetary formation and chemical evolution. This raises a fascinating possibility. If life could emerge more quickly on worlds enriched with the debris from our stellar explosion, then our sun's death might actually accelerate the development of consciousness in our corner of the galaxy. The destruction of our civilization could, paradoxically, lead to the creation of many new civilizations scattered across dozens of star systems. These hypothetical future civilizations would face an intriguing mystery when they developed the technology to study their cosmic environment. They would find themselves surrounded by unusually high concentrations of heavy elements, isotopic signatures that tell the story of a massive stellar explosion that occurred millions of years before their worlds even existed. If these alien astronomers were clever enough, they might piece together the story of our solar system's destruction. They might discover that their entire region of space was enriched by the death of a single star that once supported a world called Earth. They might even find traces of our scattered spacecraft, those lonely Voyager probes still wandering through interstellar space, carrying their golden records of human civilization. Imagine alien archaeologists studying these artifacts millions of years from now, trying to decode the messages we left behind. They would find recordings of human music, photographs of our cities, samples of our languages. These relics would tell them that somewhere in the ancient past, a species called humanity had looked up at the stars and wondered if anyone else was out there. The supreme irony would be that by the time these aliens found our messages, their own existence would have been made possible by the very catastrophe that destroyed us. They would owe their lives to our death, their consciousness to our extinction. The elements in their bodies, the rocky planets they called home, the very atoms that allowed their brains to think and wonder about the cosmos, would all be gifts from a civilization they could never meet. This cosmic pay-it-forward scenario reveals something profound about the nature of existence in our universe. Nothing truly dies. Everything gets recycled, transformed, reborn into new configurations of matter and energy. What we perceive as endings are really just transitions, cosmic phase changes that allow the universe to explore new possibilities. But even as we contemplate these vast cycles of destruction and creation, we shouldn't lose sight of what would be lost in our hypothetical solar explosion. While atoms get recycled and new worlds eventually form, the specific configurations of matter and energy that create consciousness, culture, and meaning are far more fragile. Every human language that has ever existed would disappear forever. The poetry of Shakespeare, the philosophy of Plato, the scientific insights of Einstein, all of it would be reduced to scattered atoms with no memory of the magnificent thoughts they once encoded. The accumulated wisdom of our species, built up over thousands of years of civilization, would be erased as completely as if it had never existed. Every work of art, every musical composition, every story that has ever moved the human heart would be obliterated. The Mona Lisa's enigmatic smile would become carbon dioxide and water vapor. Beethoven's Ninth Symphony would transform into thermal radiation and scattered particles. The great cathedrals and temples that represent humanity's reach toward the transcendent would melt into glowing plasma and then disperse into space. But perhaps most tragically, every relationship between conscious beings would be severed forever. Every love story, every friendship, every family bond that has given meaning to human existence would end simultaneously. The complex web of emotional connections that makes life worth living would be torn apart in a single moment of stellar violence. This is the true cost of cosmic catastrophe, not just the destruction of matter and energy, which get recycled anyway, but the obliteration of information, consciousness, and meaning. These emergent properties of complex systems are far more precious than the atoms from which they arise, and far more vulnerable to destruction. Yet even this sobering realization carries within it a kind of hope. If consciousness and meaning can emerge once from the random interactions of matter and energy, they can emerge again. The universe that created Mozart and Marie Curie and Martin Luther King Jr. once can create equally magnificent minds again, given enough time and opportunity. Our hypothetical stellar explosion would end one chapter in the cosmic story of consciousness, but it wouldn't end the story itself. Somewhere else in the galaxy, on worlds we'll never see, under the light of stars we'll never know, new forms of awareness are probably emerging right now. They're asking the same questions we ask, feeling the same wonder we feel, reaching toward the same transcendent mysteries that have always called to conscious beings. In this sense, our sun's explosion would be both ending and beginning, death and birth, tragedy and gift. It would represent the ultimate sacrifice, the destruction of everything we hold dear, so that new possibilities can emerge from the ashes of our world. The shockwave racing outward from our exploded star would carry with it more than just atoms and energy. It would carry potential, the potential for new worlds to form, new life to evolve, new consciousness to emerge. Every particle of dust scattered by our stellar death would be a seed of future possibility, a vote of confidence in the universe's ability to create something beautiful from destruction. As we watch our hypothetical solar system transform from a collection of living worlds into an expanding cloud of stellar debris, we're witnessing the universe's most fundamental creative process. This is how new realities are born. This is how the cosmos renews itself, trading old configurations of matter and energy for new ones, sacrificing the familiar to explore the unknown. The same process that would destroy our Earth has been repeating itself throughout the galaxy for billions of years. Every heavy element in your body was created by stellar explosions, just like the one we're imagining. The calcium in your teeth was scattered across space when some ancient star died in violence and glory. The iron in your blood was forged in the nuclear furnace of a massive star that lived fast, burned bright, and exploded in spectacular fashion billions of years ago. You are already the beneficiary of countless stellar sacrifices, countless cosmic catastrophes that enrich the universe with the building blocks of complexity and life. Every atom in your body carries the memory of stellar deaths that occurred long before our solar system even existed. In contemplating our sun's hypothetical explosion, we're really contemplating the cosmic processes that made our existence possible in the first place. We're imagining ourselves as participants in the same cycle of death and rebirth that has been shaping the universe since the first stars began to shine. This perspective transforms our stellar apocalypse from a story of ending into a story of continuation, from a tale of destruction into a narrative of transformation. We're not just dying. We're participating in the universe's ongoing evolution, contributing our atoms and our energy to the cosmic project of creating ever more complex and beautiful forms of organization. The expanding shockwave from our exploded sun would be like a cosmic artist's brush, painting new possibilities across the canvas of interstellar space. Where it encounters dense molecular clouds, new stars would ignite. Where it compresses and heats the interstellar medium, the chemistry of space itself would be enriched. Where it carries the scattered remnants of our world, the seeds of future Earths would be planted. In a very real sense, our destruction would be an act of cosmic love, a gift from our solar system to the universe. By dying in the most spectacular way possible, our sun would ensure that the story of matter and energy and consciousness continues in new and unexpected directions. This is the deepest lesson of our hypothetical stellar explosion. Nothing in the universe is permanent, but nothing is ever truly lost. Every ending creates the possibility of a new beginning. Every death enables new forms of life. Every destruction opens space for new creation. As we drift toward the conclusion of our cosmic catastrophe, as we watch the last traces of our solar system disperse into the infinite darkness between the stars, we can take comfort in knowing that this isn't really an ending at all. It's a transformation, a metamorphosis, a cosmic changing of the guard that ensures the universe continues its magnificent evolution toward ever greater complexity and beauty. The atoms that once made up your morning coffee will someday help form alien oceans on distant worlds. The molecules that carried your thoughts and dreams will find new configurations in the neural networks of extraterrestrial minds. The energy that once powered your beating heart will contribute to the fusion reactions in stars not yet born. In destroying us, our exploded sun would make us immortal in the only way that really matters. Not as individual consciousnesses, which are too fragile to survive such cosmic violence, but as participants in the eternal dance of matter and energy that we call the universe. The story of our sun's explosion becomes even more profound when we consider what's happening to time itself during this cosmic catastrophe. Because time, it turns out, isn't the steady, unchanging river we imagine it to be. It's more like a flexible fabric that gets stretched and compressed by gravity and motion. And during our stellar explosion, some very strange things would happen to the flow of time across our solar system. Near the surface of our exploding sun, where gravitational fields are immense and matter is accelerating to incredible velocities, time would actually slow down relative to more distant locations. If you could somehow observe from a safe distance, you would see the explosion unfolding in a kind of cosmic slow motion near the star's surface, while events farther away would appear to happen at normal speed. This time dilation effect means that different parts of our solar system would experience the explosion at slightly different rates. The inner planets, closer to the intense gravitational fields and high-energy radiation, would have their destruction stretched out over what feels like longer periods from their perspective, while the outer planets would experience their annihilation more quickly. It's a mind-bending concept that reveals how intimately connected space and time really are. The same explosion that's tearing apart the physical structure of our solar system is also warping the very fabric of space-time itself, creating ripples and distortions that would be detectable by sensitive instruments billions of miles away. These gravitational waves, ripples in space-time itself, would race outward at the speed of light, carrying with them the signature of our star's death. Any advanced civilizations within a few hundred light years of our solar system would eventually detect these waves and know that somewhere in their cosmic neighborhood, a star had died in spectacular fashion. But here's what makes this scenario truly haunting. Those gravitational waves would continue propagating through the universe for millions of years, carrying the news of our destruction to increasingly distant corners of the galaxy. Long after every atom from our solar system had been scattered and incorporated into new stars and planets, the space-time distortions from our sun's explosion would still be traveling through the cosmos like ghostly echoes of a world that once was. Imagine alien astronomers 1,000,000 years from now detecting these ancient gravitational waves and trying to piece together what caused them. They would find the telltale signature of stellar collapse and explosion, the characteristic pattern of space-time distortion that only occurs when a star destroys itself. But they would have no way of knowing that these waves carried with them the death certificate of a small blue planet that once harbored a curious species called humanity. This raises preservation across fascinating questions about the nature of information and its cosmic timescales. While the complex information that makes up human consciousness and civilization would be destroyed instantly in our stellar explosion. Simpler forms of information would survive much longer. The gravitational wave signature of our sun's death would persist for millions of years. The isotopic ratios of elements scattered by our explosion would carry chemical fingerprints of our solar system's history for billions of years. Even the orbital mechanics of nearby star systems would be subtly influenced by our explosion, creating tiny perturbations that propagate through gravitational interactions across vast distances and enormous periods of time. In a sense, our solar system's destruction would leave permanent marks on the structure of our local galactic neighborhood, changes so subtle they might never be detected, but so persistent they would outlast entire geological epochs on distant worlds. This cosmic persistence of information reveals something beautiful about the universe. Even the most violent and destructive events leave traces, create patterns, establish new baselines that influence everything that comes after. Our hypothetical stellar explosion wouldn't just destroy our world. It would become part of the historical record of the galaxy itself, woven into the fabric of spacetime and the chemical composition of interstellar space. But let's bring our focus back to something more immediate and visceral. What would it actually sound like when a star explodes? This might seem like a silly question since sound can't travel through the vacuum of space, but the answer reveals fascinating details about the physics of stellar destruction and the nature of sound itself. On Earth, during those first 8 minutes before the light from the explosion arrives, you would hear absolutely nothing unusual. The explosion would be happening 93 million miles away in the complete silence of space, with no medium to carry sound waves to your ears. The normal sounds of your morning routine, traffic outside your window, birds singing in the trees, would continue exactly as they always had. But when the shockwave finally reaches Earth's atmosphere, everything changes. The collision between the expanding wall of stellar debris and our planet's thin envelope of air would create sound on a scale beyond human comprehension. It wouldn't be a single loud noise, like a thunderclap or an explosion. It would be a complex symphony of destruction, as different layers of our atmosphere got heated and compressed at different rates. The first sounds would be in frequencies so low that you would feel them more than hear them. Deep, rumbling vibrations that would seem to come from inside your own body as the entire planet began to resonate like a struck bell. These infrasonic waves would travel through the ground and through your bones, creating sensations that no human had ever experienced. As the atmosphere continued to heat and expand, higher frequencies would join this cosmic bass note. The sound of nitrogen and oxygen molecules breaking apart under extreme temperatures would create a hissing, crackling noise like bacon in a pan, but amplified to planetary scales. The sound of water vapor flashing to steam would add its own contribution, a whooshing roar like standing next to a massive waterfall. But perhaps the most haunting sound would be silence itself. As our atmosphere got stripped away into space, as the medium that carries sound waves got torn from our planet, the cacophony of destruction would gradually fade, not because the destruction was slowing down, but because there would no longer be any air left to carry the sound of our world ending. The transition from deafening noise to absolute silence would happen surprisingly quickly. One moment you would be surrounded by the loudest sounds in human history. The next moment you would be enveloped in the complete quiet of airless space. It would be like having the volume of the entire world suddenly turned down to zero. This progression from sound to silence perfectly captures the nature of our stellar explosion. It starts with overwhelming sensory bombardment, more light and heat and noise than biological systems can process, and ends with the complete absence of everything that makes a world livable. From chaos to emptiness in the span of a few hours. The psychological impact of experiencing these impossible sounds would be profound. Our brains are calibrated to interpret certain sounds as dangerous, others as safe, still others as beautiful or comforting. But the sounds of planetary destruction would be so far outside normal human experience that our minds would have no framework for processing them. You might find yourself feeling simultaneously terrified and fascinated, overwhelmed by the sheer scale of the acoustic experience, while also recognizing that you were hearing something that no human ear had ever detected before. These would be the first and last sounds of their kind, a unique acoustic signature of stellar death that would never be repeated in exactly the same way. Some of the sounds might even be beautiful in their strangeness. The resonant frequencies of a planet-sized atmosphere being heated to thousands of degrees could create harmonic progressions unlike anything in terrestrial music. The Doppler shifts caused by massive air movements could produce gliding tones that sweep across the entire audible spectrum. For brief moments, Earth might sing its own death song in frequencies that would move you to tears if you lived long enough to hear them. But beauty and terror often walk hand in hand in cosmic events, and our stellar explosion would be no exception. The same acoustic phenomena that create moments of strange musical beauty would also be tearing apart the very air that makes sound possible. Every note in Earth's final symphony would bring us closer to the silence that follows. As we contemplate these impossible sounds, we're forced to confront another aspect of our hypothetical catastrophe: the complete destruction of context. Every sound you've ever heard has occurred within the framework of a stable planetary environment. The rustle of leaves requires trees and wind. The crash of ocean waves requires liquid water and gravity. The voices of people you love require vocal cords and air, and the complex chemistry of life. When our sun explodes, it wouldn't just destroy these individual sources of sound, it would destroy the entire context that makes sound meaningful. There would be no more wind because there would be no more atmosphere, no more ocean waves because there would be no more liquid water, no more voices because there would be no more life. This contextual destruction extends far beyond sound to encompass every aspect of human experience. The explosion wouldn't just kill us, it would obliterate the entire framework of meaning that makes human existence comprehensible. Colors would lose their significance because there would be no more light to create them. Temperatures would become irrelevant because there would be no more matter to be warm or cold. Distance and direction would lose their importance because there would be no more stable reference points to navigate by. In a very real sense, our stellar explosion would destroy not just our world, but our entire way of understanding the world. Every concept we use to make sense of reality, from the simple distinction between up and down to the complex relationships between cause and effect, depends on the existence of a stable planetary environment with consistent physical laws. When that environment gets obliterated, when those physical constants get overwhelmed by forces of unimaginable magnitude, the very categories we use to think about existence become meaningless. We wouldn't just be dying, we would be watching the death of meaning itself. This philosophical dimension of our cosmic catastrophe reveals why stellar explosions are so profoundly unsettling to contemplate. They don't just threaten our physical survival, they threaten our conceptual survival, our ability to make sense of our place in the universe. They force us to confront the possibility that all of our carefully constructed frameworks for understanding reality are just temporary conveniences, useful only as long as we happen to live on a stable planet orbiting a well-behaved star. But even as we grapple with this existential vertigo, we can find comfort in recognizing that meaning and context aren't really destroyed by stellar explosions. They're transformed, relocated, redistributed across space and time in ways that we're only beginning to understand. The atoms that once participated in creating the sound of your laughter will someday participate in creating new forms of acoustic beauty on worlds we'll never see. The molecules that once carried the chemical signals of human emotion will find new roles in alien biochemistries we can't imagine. The energy that once powered human consciousness will contribute to new forms of awareness that might be far more sophisticated than anything our species ever achieved. Our stellar explosion would end one particular configuration of matter and energy that we call human civilization, but it would simultaneously create the raw materials for countless new configurations, countless new possibilities for meaning and beauty and consciousness to emerge. This is the ultimate paradox of cosmic destruction. What appears to be ending is actually transformation. What seems like loss is actually redistribution. What looks like death is actually the universe's way of exploring new forms of life. As our sun continues its hypothetical explosion, as the shockwave carries the scattered remains of our solar system deeper into interstellar space, we're witnessing not just the end of our story, but the beginning of countless other stories. Every atom blasted away from our dying world becomes the opening sentence of a new cosmic narrative. The calcium from your bones might help form the crust of a terrestrial planet orbiting a red dwarf star, providing the geological foundation for continents and mountains that will shape the evolution of alien landscapes for billions of years. The phosphorus from your DNA might become part of the biochemistry of extraterrestrial life forms that develop entirely different approaches to storing and transmitting genetic information. The iron from your blood might end up in the core of a gas giant planet, creating magnetic fields that protect that world's moons from cosmic radiation, enabling the development of complex chemistry in subsurface oceans. The carbon from your thoughts and dreams might find itself incorporated into atmospheric compounds that create greenhouse effects on distant worlds, making those planets warm enough to support liquid water on their surfaces. Each scattered atom carries with it a kind of cosmic heritage, a history of having been part of something complex, remarkable, and conscious. When these atoms eventually find new homes in alien star systems, they bring with them the accumulated experience of having participated in the grand experiment of Earth-based life. In this sense, our stellar explosion becomes an act of cosmic seed dispersal on the grandest scale imaginable. Instead of a single planet sending out spores or pollen to create new life nearby, an entire solar system gets broken apart and scattered across hundreds of cubic light years, planting the chemical seeds of future worlds throughout our local region of the galaxy. The irony is profound. The same explosion that ends human civilization also ensures that the elements essential for life get distributed more widely than they ever could have been otherwise. Our destruction becomes the universe's way of spreading the building blocks of consciousness across vast distances, giving future forms of awareness the chemical tools they need to emerge and flourish. But this cosmic dispersal process isn't random or chaotic. It follows elegant patterns determined by the physics of stellar explosions and the gravitational architecture of our galactic neighborhood. The heaviest elements, forged in the final moments of our sun's nuclear burning, get ejected at the highest velocities and travel the farthest distances. The lighter elements get swept up by the expanding shockwave and deposited in nearby molecular clouds where new stars are already beginning to form. This creates a kind of cosmic stratification, with different elements settling into different regions of space based on their mass and the energy imparted to them by the explosion. Future star systems that form from this material will inherit different chemical signatures depending on which part of the expanding debris cloud they happen to condense from. Some new worlds might be unusually rich in heavy elements, giving them the potential to develop complex rocky surfaces and diverse mineralogies much earlier in their evolutionary history than Earth did. Other worlds might be dominated by lighter elements, creating gas giant planets with unusual atmospheric compositions and exotic chemistry in their upper cloud layers. The diversity of possible outcomes is staggering. Our single stellar explosion could eventually give rise to dozens of new star systems, each with its own unique collection of planets and moons, each exploring different combinations of the chemical elements that once made up our solar system. Some of these new worlds might develop conditions suitable for life within just a few 100 million years of their formation. Others might remain sterile for billions of years before finally achieving the delicate balance of conditions necessary for complex chemistry to emerge. Still others might develop forms of organization and complexity that we would barely recognize as life at all. The beautiful uncertainty of this process reflects something fundamental about the nature of cosmic evolution. Every stellar explosion is simultaneously an ending and a beginning, a destruction and a creation, a closing of one chapter in the universe's story, and an opening of countless new chapters that explore previously unimaginable possibilities. As we watch our hypothetical solar system complete its transformation from a collection of stable orbiting worlds into an expanding cloud of enriched interstellar material, we're witnessing the universe's most fundamental creative process in action. This is how new realities are born. This is how the cosmos reinvents itself, trading familiar configurations of matter and energy for exotic new arrangements that push the boundaries of what's possible. The expanding shockwave from our exploded sun carries with it more than just scattered atoms and thermal energy. It carries potential energy, gravitational energy, magnetic field energy, and most importantly, the kind of organized complexity that can only emerge from the violent mixing and heating that occurs during stellar explosions. New isotopic ratios get created in the extreme conditions near our sun's surface during the explosion. Unusual crystalline structures form as different elements get compressed and cooled at unprecedented rates. Complex organic molecules get synthesized in the turbulent mixing zones where different temperature and pressure regimes collide and interact. All of this newly created complexity gets blasted into interstellar space, where it will drift for thousands or millions of years before eventually settling into new gravitational wells and beginning the slow process of assembling into new forms of organization. The universe doesn't just recycle old materials. It uses the energy of destruction to create entirely new forms of matter and structure that never existed before. This is why stellar explosions are so crucial to the ongoing evolution of the cosmos. They're not just cosmic disasters that destroy existing worlds. They're cosmic laboratories that synthesize new chemical possibilities and scatter them across vast volumes of space, ensuring that the universe continues to explore new forms of complexity and organization. Our hypothetical stellar explosion would add our own unique contribution to this cosmic laboratory. The specific isotopic signatures created by billions of years of chemical evolution on Earth would get blasted into space, carrying with them the molecular fingerprints of a world that once supported an incredibly diverse and sophisticated biosphere. Future alien geochemists studying the composition of their worlds might discover trace amounts of elements with isotopic ratios that could only have been produced by long-term biological processes. They might find chemical signatures of photosynthesis, evidence of oxygen-producing organisms, molecular fossils of complex organic chemistry that once flourished on a planet they'll never see. These chemical ghosts of our world would tell a story of life's incredible creativity and persistence, even to beings who might never develop the technology to trace these elements back to their ultimate source. In studying the rocks and minerals of their own worlds, alien scientists might unknowingly be studying the remains of Earth's biosphere, scattered across space and time by our sun's magnificent death. The poetic justice of this scenario is breathtaking. Our world, which developed consciousness and scientific understanding over billions of years of evolution, would become a permanent part of the chemical heritage of countless future worlds. Every new planet that forms from the debris of our explosion would carry within its very substance the atomic memory of a species that once looked up at the stars and wondered about its place in the universe. In death, we would achieve a kind of immortality that no individual consciousness could ever attain. Not the preservation of our thoughts and memories and personalities, which are far too fragile to survive such cosmic violence, but the preservation of our essential nature as complex, organized, conscious arrangements of matter and energy. The universe would remember us not as individuals, but as a successful experiment in the organization of matter into forms capable of self-awareness and wonder. And that memory would be encoded not in books or monuments or digital storage devices, all of which would be vaporized in the stellar explosion, but in the very atoms and molecules that make up the substance of future worlds. This atomic memory would influence the development of those future worlds in ways both subtle and profound. Planets enriched with the scattered remains of our biosphere would have access to chemical tools and processes that might accelerate their own journey toward complexity and life. The elements that once participated in Earth's incredible experiment with consciousness would bring to their new homes a kind of chemical wisdom, an accumulated understanding of how matter can organize itself into increasingly sophisticated forms. In contemplating this cosmic inheritance that our exploded sun would leave behind, we begin to understand that stellar destruction isn't really about endings at all. It's about transformations so profound and far-reaching that they reshape the very possibilities for existence regions in entire of the galaxy. Our stellar explosion would be like a cosmic artist taking apart a magnificent painting and using its pigments to create hundreds of new masterpieces, each one unique, each one exploring different combinations of color and form and meaning. The destruction of one beautiful thing becomes the creation of countless other beautiful things, each building on the achievements of what came before, while simultaneously reaching toward entirely new forms of beauty. This is the deepest truth about our hypothetical catastrophe. It reveals the universe as an endlessly creative system that uses destruction as a tool for creation, death as a mechanism for new life, endings as opportunities for new beginnings. Nothing is ever truly lost, because everything is constantly being transformed into something new and unexpected and wonderful. As we drift toward our conclusion, as we watch the last traces of our familiar solar system disappear into the infinite darkness between the stars, we can take comfort in knowing that this ending is really a transformation. This death is really a birth. This apparent catastrophe is really the universe's way of ensuring that the story of consciousness and complexity and beauty continues in forms we never could have imagined. The atoms that once made up your morning coffee will someday help create alien oceans under foreign skies. The molecules that carried your deepest thoughts will find new configurations in extraterrestrial minds that might be far more sophisticated than anything humanity ever achieved. The energy that once powered your heart will contribute to the fusion reactions in stars not yet born, providing the light that nurtures forms of life we can't even begin to conceive. Our sun's explosion wouldn't just scatter atoms randomly across the void. The expanding shockwave would create complex patterns of density and temperature as it interacted with the existing interstellar medium. These patterns would act like cosmic fingerprints, creating unique structures in space that would persist for millions of years. Imagine vast filaments of enriched gas stretching across dozens of light years, glowing faintly with the thermal radiation of our scattered world. These filaments would become highways star formation for future, channels where gravity could more easily gather material together to furnaces ignite new nuclear. The geometry of our destruction would literally reshape the architecture of our local galactic neighborhood. Within these glowing filaments, something extraordinary would begin to happen. The turbulence created by our stellar explosion would compress pockets of gas to densities high enough to trigger gravitational collapse. But unlike the slow, gentle process of normal star formation, which takes millions of years, this shock-induced collapse would happen much more rapidly. New stars would begin to ignite within just a few thousand years of our sun's death, fed by material enriched with the heavy elements from our destroyed worlds. These stars would be fundamentally different from our sun, born already rich in the carbon, oxygen, silicon, and iron that took our solar system billions of years to accumulate through slow stellar nucleosynthesis. The planets that form around these new stars would be alien in ways that challenge our understanding of planetary evolution. Rocky worlds could develop complex mineralogies within their first few 100 million years, creating geological processes and surface chemistries that Earth never experienced. The accelerated timeline of complexity would open up possibilities for forms of life that could emerge much earlier and evolve much faster than anything in our solar system's history. But the influence of our explosion would extend far beyond just creating new star systems. The expanding shell of stellar debris would encounter other existing stars, planets, and cosmic structures throughout our region of space. When our shockwave reaches nearby stellar systems, it would deliver a payload of heavy elements and energy that could dramatically alter the evolution of those worlds. Consider a star system located 50 light-years from our Sun, currently home to several rocky planets in various stages of atmospheric development. When our shockwave arrives, carrying with it the scattered remains of Earth's biosphere, it would deposit complex organic molecules and rare isotopes onto those distant worlds. A planet that might have taken billions of years to develop the chemical precursors for life could suddenly find itself enriched with ready-made building blocks of complexity. Amino acids synthesized in the violent mixing zones of our stellar explosion would rain down on alien surfaces, seeding those worlds with molecular tools that evolution on Earth took eons to develop. This cosmic contamination wouldn't guarantee the emergence of life, but it would dramatically alter the probability landscape for biological evolution. Worlds that might never have developed complexity on their own could find themselves jump-started by the chemical gifts delivered by our expanding shockwave. The ethical implications of this scenario are profound and unsettling. Our sun's explosion would essentially be performing uncontrolled experiments on countless worlds throughout our galactic neighborhood. We would be inadvertently seeding dozens of star systems with Earth's biochemical legacy, potentially influencing the evolution of alien life forms in ways we could never predict or control. Some philosophers might argue that this represents a form of cosmic imperialism, our dead civilization imposing its chemical signature on virgin worlds that might have developed entirely different approaches to complexity and organization. Others might see it as a beautiful form of cosmic altruism, our destruction providing gifts that help other worlds achieve their own unique forms of consciousness and wonder. The truth is probably somewhere between these extremes. Our scattered atoms would become part of alien worlds, but those worlds would integrate our chemical legacy according to their own unique physical conditions and evolutionary pressures. The carbon form, the structural from our DNA, might help molecules of silicon-based life. The phosphorus from our cell membranes might become part of entirely different energy storage systems in alien biochemistries. This integration process would create hybrid worlds, planets whose evolution reflects both their own indigenous processes and the foreign influence of our scattered solar system. These worlds would be neither purely alien nor recognizably Earth-like, but something entirely new, unique combinations and foreign influences that of local push the boundaries of what we consider possible. The timescales involved in this cosmic cross-pollination are staggering. Our shockwave would take thousands of years to reach nearby star systems, millions of years to traverse our entire local galactic region. The complex chemistry delivered by our explosion would then take millions or billions of additional years to be incorporated into new forms of organization and life. By the time alien civilizations might emerge from worlds enriched by our destruction, so much time would have passed that they would have no way of knowing their debt to a small blue planet that once orbited a star called Sol. They would study their own origins and development without ever realizing that their existence was made possible by the death of a species that once wondered whether anyone else was out there among the stars. This cosmic anonymity adds a layer of poignancy to our hypothetical destruction. We would become the unknown benefactors of countless future civilizations, our sacrifice enabling their existence while receiving no recognition or gratitude for our contribution. It's the ultimate expression of selfless giving, though entirely involuntary on our part. But perhaps this anonymity is appropriate. True gifts don't require acknowledgement or reciprocity. The most generous acts are often those performed without any expectation of recognition or reward. Our sun's explosion would represent the ultimate expression of this principle. A cosmic gift so vast and far-reaching that its recipients would never even know they had received it. The expanding shell of our stellar debris would continue to influence galactic evolution for millions of years, creating a cascade of consequences that ripple through space and time in ways that become increasingly difficult to trace back to their original source. New star systems would form, evolve, and potentially die, each one carrying forward some portion of our chemical legacy while adding their own unique contributions to the cosmic mix. Eventually, some of the atoms that once made up your body might find themselves incorporated into the explosion of another star, billions of years in the future. The calcium from your bones could participate in multiple cycles of stellar death and rebirth, each time getting mixed with new elements and scattered to new regions of the galaxy. This multi-generational cosmic recycling creates a kind of atomic genealogy that connects all matter in the universe across vast distances and timescales. Every atom has a history, a lineage that stretches back to the earliest moments after the Big Bang and forward to futures we can't even imagine. Your atoms have already lived through at least one complete cycle of stellar death and rebirth. The elements that make up your body were forged in the nuclear furnaces of ancient stars that died long before our solar system even existed. Those stellar explosions scattered the building blocks of complexity across space, eventually allowing them to be incorporated into the gas cloud that would become our sun and planets. In our hypothetical scenario, your atoms would be embarking on their next great journey, being scattered once again to help form new worlds and new possibilities for organization and consciousness. They would carry with them the accumulated experience of having been part of something remarkable and complex and aware, even though that experience would be encoded in ways too subtle for future civilizations to detect. This perspective transforms our stellar explosion from a story of ending into a chapter in an ongoing cosmic epic that spans the entire history of the universe. We're not just dying. We're participating in the eternal dance of matter and energy that creates, destroys, and recreates the cosmos in an endless cycle of transformation and renewal. The expanding shockwave from our exploded sun would eventually encounter the boundaries of our local galactic environment, regions where the interstellar medium becomes thinner and the influence of other nearby stars begins to dominate. At these boundaries, our stellar debris would mix with material from other sources, creating complex chemical gradients that reflect the combined influence of multiple stellar generations. These mixing zones would become laboratories for exotic chemistry, regions where elements from different stellar sources encounter each other under conditions that don't exist anywhere else in the galaxy. New molecular species would form, crystalline structures would emerge, and complex organic chemistry would unfold in the cold depths of interstellar space. Some of these interstellar chemical reactions would create molecules of staggering complexity, organic compounds that approach the threshold of what we might consider primitive life. These molecules would drift through space for millions of years, stable in the near absolute zero temperatures of the void, waiting for the right conditions to participate in even more complex organizational schemes. When these prebiotic molecules eventually encounter new planetary surfaces, they would bring with them chemical capabilities that far exceed what simple planetary chemistry could produce on its own. Worlds that receive deposits of this interstellar organic material would have access to molecular tools and processes that could dramatically accelerate their journey toward complexity and life. This creates the possibility of a kind of galactic ecosystem where the chemical products of stellar death and interstellar chemistry create networks of influence and exchange that span vast distances and timescales. Our sun's explosion would be one node in this vast network, contributing its own unique chemical signature while also carrying forward the influences of countless previous stellar generations. The beauty of this galactic ecosystem lies in its incredible diversity and unpredictability. Every stellar explosion creates its own unique mix of elements and energy, which then interacts with the existing interstellar environment in ways that depend on countless local factors. The result is a cosmos where no two regions of space have exactly the same chemical history or evolutionary potential. Our explosion would add its own thread to this cosmic tapestry, creating patterns and possibilities that would influence galactic evolution for millions of years to come. The specific combination of elements, energy, and timing that characterizes our stellar death would create opportunities for forms of organization and complexity that might never emerge anywhere else in the universe. In contemplating this vast web of cosmic influence and exchange, we begin to understand that our sun's explosion wouldn't just be an isolated catastrophe affecting our local solar system. It would be a significant event in the ongoing evolution of our entire galactic region. An event whose consequences would ripple through space and time in ways that shape the development of countless future worlds. The atoms that once carried your thoughts and dreams would become part of this grand cosmic conversation, contributing their own unique voice to the ongoing dialogue between matter and energy that we call the universe. In death, we would achieve a kind of immortality that no individual consciousness could ever attain, becoming permanent participants in the eternal cosmic dance of creation and transformation. As the shock wave from our exploded sun continues its journey through interstellar space, it would begin to encounter structures and phenomena that exist on scales even larger than individual star systems. Vast molecular clouds, some containing enough material to form thousands of new stars, would be compressed and heated by our passing debris, triggering episodes of star formation that could reshape entire regions of the galaxy. These molecular clouds, some of which are hundreds of light years across, represent the raw material from which future generations of stars and planets will form. When our shockwave encounters them, it would be like striking a cosmic match, igniting processes of gravitational collapse and nuclear fusion that would light up vast regions of space with the glow of newly born stars. The scale of this triggered star formation would be truly breathtaking. Our single stellar explosion could be responsible for the birth of hundreds or even thousands of new stars, each one destined to follow its own evolutionary path through the cosmos. Some would be massive and short-lived, burning through their nuclear fuel in just a few million years before exploding in their own spectacular supernovas. Others would be small and long-lived, providing stable sources of energy for billions of years of planetary evolution. This cascade of star formation would create what astronomers call a stellar association, a loose grouping of stars that share a common origin and initial motion through space. Future galactic archaeologists might be able to identify these stars as the offspring of our explosion, recognizing their common chemical signatures and similar ages even after they had dispersed across hundreds of light years. But the influence of our stellar death would extend even beyond triggering new star formation. The energy and turbulence created by our shockwave would disrupt the existing structure of the interstellar medium, creating new patterns of density and motion that would influence galactic dynamics for millions of years. Spiral density waves, those mysterious structures that create the beautiful spiral arms we see in galaxies like our own Milky Way, could be altered by the energy injection from our explosion. The delicate balance of gravitational forces and pressure waves that maintains these spiral patterns could be disrupted, potentially triggering reorganization of stellar orbits throughout our galactic neighborhood. This galactic scale influence of our stellar explosion reveals something profound about the interconnected nature of cosmic evolution. Nothing exists in isolation. Every event, no matter how localized it might seem, sends ripples through the fabric of space and time that eventually influence structures and processes on the largest scales imaginable. Our sun's death would become part of the ongoing story of galactic evolution, one thread in the vast tapestry of gravitational interactions, stellar births and deaths, and chemical enrichment that shapes the development of entire spiral arms. The atoms that once made up our familiar solar system would participate in processes so vast and long-term that they approach the scale of cosmic evolution itself. In this context, our hypothetical catastrophe begins to look less like an age-changing ending and more like a transition of the guard that allows the universe to explore new possibilities and arrangements of matter and energy. We would be trading our current existence as inhabitants of a stable planetary system for a new role as participants in galactic evolution, contributors to the ongoing cosmic experiment in organization and complexity. The perspective shift required to appreciate this transformation is enormous. We're so accustomed to thinking of ourselves as individuals living on a single planet that it's difficult to imagine our atoms and energy becoming part of galactic-scale processes that unfold over millions of years. But this broader perspective reveals the true scope of our cosmic citizenship. We're not just residents of Earth or even of our solar system. We're temporary arrangements of matter and energy that belong to the galaxy itself, borrowings from the cosmic inventory of elements and forces that will eventually be returned to participate in new and different forms of organization. Our stellar explosion would simply be the mechanism by which this return occurs, the process by which our local arrangement of matter gets redistributed for use in new cosmic experiments. This galactic perspective on our destruction helps explain why stellar explosions are so crucial to cosmic evolution. They're not just random acts of violence that destroy existing structures. They're essential mechanisms for redistributing matter and energy on the scales necessary to drive ongoing galactic development. Without stellar explosions, Heavy elements would remain locked up in the cores of dying stars, unavailable for incorporation into new planetary systems. Without the energy injection from these cosmic catastrophes, the interstellar medium would remain static and uniform, unable to support the complex chemistry and dynamic processes that lead to new star formation. Our sun's explosion would be fulfilling this essential cosmic function, taking the heavy elements that our solar system has spent billions of years accumulating and making them available for use by future generations of stars and planets. We would be participating in the universe's most fundamental recycling program, ensuring that the building blocks of complexity continue to be available for new experiments in organization and consciousness. The beauty of this cosmic recycling lies in its creative potential. The same elements that once participated in human civilization would someday help create forms of organization and awareness that we can't even begin to imagine. The carbon that once encoded our genetic information might become part of silicon-based life forms that think in ways completely alien to human consciousness. The oxygen that once filled our lungs might help create atmospheric chemistries that support forms of life based on entirely different energy sources and metabolic processes. This transformation of our familiar elements into alien forms of organization represents the universe's incredible creativity and resourcefulness. Nothing is ever wasted. Nothing is ever truly destroyed. Everything gets recycled, reused, reimagined into new configurations that explore previously unexplored possibilities for matter and energy to organize themselves into complex and beautiful patterns. As we approach the final stages of our cosmic journey, as we watch our solar system complete its transformation from a collection of stable worlds into an expanding cloud of enriched interstellar material, we're witnessing the universe's most fundamental creative process at work. This is how new realities are born, how the cosmos reinvents itself, how matter and energy explore the infinite space of possible organizations and arrangements. The shockwave from our exploded sun, now millions of miles in diameter and still expanding at thousands of miles per second, carries with it more than just the scattered atoms of our familiar world. It carries the accumulated experience of billions of years of cosmic evolution, the chemical wisdom gained from the successful experiment in complexity and consciousness that we call Earth. This experience, encoded in isotopic ratios and molecular structures too subtle for any observer to detect, would influence the development of countless future worlds in ways both profound and invisible. Every new planet that forms from our scattered debris would inherit not just our chemical elements, but the organizational patterns and structural relationships that those elements learned during their time as part of a living, conscious world. In death, we would become teachers for the universe, our destruction serving as a cosmic classroom where matter and energy learn new lessons about the possibilities for organization and awareness. The forms of life and consciousness that eventually emerge from worlds enriched by our explosion would be fundamentally different from anything that evolved on Earth. But they would carry within their very atoms the memory of our experiment with existence. This atomic memory would influence their development in ways so subtle and indirect that they would never recognize our contribution to their evolution. But the influence would be real nonetheless, woven into the fabric of their reality at the most fundamental level imaginable. We would achieve a kind of immortality that transcends individual consciousness, becoming permanent participants in the ongoing cosmic exploration of what it means to exist, to be aware, to wonder about one's place in the vast and mysterious universe. The expanding shell of our stellar debris would continue its journey through space for millions of years, creating new stars, enriching interstellar clouds, triggering episodes of galactic evolution that would reshape entire regions of the Milky Way. And somewhere in that vast, expanding wave of transformation and possibility, the atoms that once made up your morning thoughts would begin their next great adventure in the eternal dance of cosmic becoming. And so we reach the end of our impossible journey, having witnessed the complete transformation of everything we've ever known into something vast and magnificent and utterly alien. We've watched our familiar sun tear itself apart in a display of violence so spectacular that it defies human comprehension. We've seen our precious Earth, that blue marble suspended in the cosmic dark, get stripped down to its component atoms and scattered across hundreds of cubic light-years of space. But here's what makes this thought experiment so profoundly beautiful. What appeared to be the ultimate ending was actually the ultimate beginning. Every atom that once made up your body, every molecule that carried your thoughts, every particle of matter that participated in the grand experiment we call human civilization, would survive this cosmic catastrophe to become part of something entirely new and wonderful. The calcium from your bones will help build alien mountains under foreign stars. The carbon from your DNA will encode new forms of genetic information in biochemistries we can't imagine. The oxygen that once filled your lungs will nurture forms of life so sophisticated and beautiful that they would seem like magic to our current understanding. This is the deepest truth about existence in our universe. Nothing is ever truly lost. Everything is constantly being transformed, recycled, reborn into configurations of matter and energy that push the boundaries of what we thought was possible. Our sun's explosion wouldn't represent death. It would represent the most generous act of creation imaginable, scattering the seeds of future consciousness across vast regions of space. Tonight, as you step outside and look up at that familiar star hanging in our sky, remember this: you are already made of stellar debris from ancient explosions that occurred billions of years ago. You are the universe's way of experiencing itself, a temporary arrangement of cosmic matter that has achieved the extraordinary feat of self-awareness and wonder. And whether our sun explodes tomorrow or continues burning for another 5 billion years, you are part of something magnificent and eternal. Your atoms will dance through the cosmos long after your consciousness has faded, participating in forms of beauty and complexity that we can't even begin to conceive. Sweet dreams, fellow travelers in this cosmic story. The universe continues its ancient dance of creation and transformation around you, and you are part of that dance, now and always, in ways both profound and beautiful.